The wall is behind your back. Are you sure it's there? Science says no. Not until you turn around. At the most fundamental level, the particles that make up the wall exist only as a blurry blueprint, a cloud of pure probability. It is the very act of your observation that forces this probability to collapse into one specific outcome. This isn't a theory, it's an experimental fact, confirmed many times over. It seems as if the system generates the world only within your field of view to conserve computational resources. If reality is assembled specifically for us at the moment of observation, then who or what is the programmer? And this isn't the only glitch in our system. Are we explorers of the universe, or are we users inside a program? We face two fundamental contradictions. On one hand, our world requires objects to have a definite place and properties. On the other, these objects are composed of particles that exist in all places at once until they are measured. The answer to this question awaits us in Section 3. The second contradiction is that the universe has a set of physical constants fine-tuned with surgical precision for the existence of life. The chance of them arising randomly is so small it's compared to a hurricane sweeping through a junkyard and accidentally assembling a complete Boeing 747 from the scrap. An infinite number of other, more probable combinations would lead to absolute emptiness. This doesn't look like a coincidence, but like a deliberate design. The solution to this fine-tuning puzzle will appear in Section 7. These questions are not a mind game, but real problems in physics, and the simulation hypothesis offers a single, albeit frightening, explanation for them. For many, the introduction to this idea began with the movie The Matrix, safe, entertaining science fiction. But in 2003, Oxford philosopher Nick Bostrom published his work, and the idea moved from movie theaters to academic lecture halls. Soon, Elon Musk picked it up, bringing it into the boardrooms of tech giants. We will follow the same path together, from a Hollywood fairy tale to the scientific reality of Oxford. We will demonstrate the rigorous logic and physical evidence that compel the brightest minds on the planet to take this seriously. This is not just an intellectual exercise. It is a tool that will force you to rethink the nature of consciousness, reality, and the meaning of your own existence. To ensure you don't get lost in this rabbit hole, here is a map of our journey. It is built around 6 key pieces of evidence. In just 4 minutes, we will detonate philosopher Nick Bostrom's logical bombshell, a rigorous argument proving that one of 3 shocking conclusions about humanity must be true. And the most probable of them is that we are in a simulation. Around the 10th minute, we will go in search of our reality's pixel. We will show physical evidence indicating that our world has a finite resolution, just like a digital image. Toward the end, at the 19th minute, we will reveal why the speed of light is not a fundamental law of nature, but rather a technical limitation of the processor running our universe. In 4 minutes, you will understand the logical trap from which, according to philosophers, humanity has no escape. Why does Elon Musk, a man who builds rockets based on the strictest calculations, claim that the chance we are not living in a simulation is 1 in billions? This isn't a sudden bout of madness, but the result of a cold, logical chain of reasoning known as Bostrom's trilemma. It works like an old apothecary's scale. On one pan, we place the first option: almost all civilizations go extinct before they can create simulations. This is a simple, pessimistic explanation. On the other pan, we place the second option: civilizations reach this power, but, for some reason, are not interested in creating simulations of their ancestors. But our own reality refutes this thesis. We are moving toward creating more, not fewer simulations. And if neither of these 2 pans outweighs the other, the third one, the simulation, inevitably becomes the heaviest. If we are unlikely to go extinct, and unlikely to lose interest, then by simple statistics, the number of simulated worlds will vastly exceed the number of base realities. This means we are almost certainly already in one of them. It's not a choice, it's a logical checkmate. This logical trap explains why the hypothesis migrated from science fiction to the offices of physicists. In 2003, Oxford philosopher Nick Bostrom published an article titled, "Are You Living in a Computer Simulation?" At the time, it was a purely speculative exercise, but reality began to catch up with philosophy. Computing power doubles approximately every 2 years according to Moore's law. The development of virtual reality and artificial intelligence has turned an abstract idea into a concrete technological roadmap. What was philosophy in 2003 has become an engineering challenge for today's IT giants. The power of Bostrom's argument is that it doesn't require belief in gods or aliens. It only requires belief in 2 things we see every day: statistics and technological progress. But the scientific community had a powerful counterargument that, it seemed, should have buried this idea forever. Why is an idea that is logically flawless still not considered a full-fledged scientific theory? The answer is one word: falsifiability. This is the foundation of the scientific method, formulated by Karl Popper. If a theory cannot, in principle, be disproven by an experiment, it lies outside the realm of science. And the simulation hypothesis seems to be just that. Any discovery, any experiment can be declared to be simply part of the code. This is a dead end. But the picture changes if we shift our focus. Instead of trying to hack the system, we can look for its internal limitations. We can search not for an exit, but for seams, bugs, and performance limits. The search for evidence of a simulation is like the work of a geologist. He doesn't try to break the planet. He looks for fault lines and layers of rock that tell the story of its internal structure. And the most striking candidate for such a fault line in the fabric of reality has been studied by physicists for decades. Have you ever encountered an inexplicable glitch in your daily life? If we are in a simulation, why would the creators calculate every single atom in the universe? That would be a colossal waste of computational resources. Or, perhaps they don't. One might assume they have unlimited power, but the reality of programming suggests otherwise. Resource optimization is a fundamental principle of any computational system, from a video game to a scientific model. No sane programmer would waste resources processing something the user doesn't see. This is similar to how our peripheral vision works. We see the world clearly only in the center, while the rest is filled in by the brain in low resolution. What if our universe operates on the same principle? What if it doesn't calculate the reality behind your back, but generates it only at the moment you look at it? This crazy idea is not a fantasy, but a direct consequence of the most famous and bizarre experiment in the history of physics. It's called the double-slit experiment. A particle of matter flying toward a screen behaves like a predictable ball when it is being watched. But as soon as observation stops, it transforms into a wave, passing through all possible slits simultaneously. When electrons are fired one by one, they still create an interference pattern on the final screen, as if each one knew about the existence of the second slit and interacted with itself. But place a detector at the slit to find out exactly where the electron passed, and the wave pattern instantly disappears. Reality changes when it is being watched. This isn't just a curiosity. It is literally rendering on demand. The system doesn't waste resources calculating a complex wave if you request a specific result. Perhaps all these quantum oddities are just exotic features of the microworld, safely isolated from our everyday reality. At first glance, yes. On our scale, the effect of decoherence hides quantum uncertainty from us. We see a chair as a chair, not as a cloud of probabilities, and this creates a false sense of security. But every one of the approximately 7 octillion atoms in your body, every brick in your house, is made of these very particles. There is no boundary where the strange world ends and the normal one begins. Our normality is merely the averaged-out result of trillions of quantum processes. You are not built from solid bricks, but from blueprints that materialize into bricks only upon interaction. This fundamentally changes our role in the universe. When you are not looking at your face in the mirror, are you sure you have one? Or does only a mathematical probability of its existence exist? Our basic programming, naive realism, insists that the world exists objectively, independent of us. But quantum mechanics directly states that an object's properties, such as its position or velocity, do not exist before the act of measurement. Science is shattering our most basic illusion. We are not just passive observers in the movie theater of the universe. We are the operators who, with our gaze, compel the projector to render a frame from an infinite set of possibilities. Physicist John Wheeler even proposed the term participatory universe to describe this idea. But if reality is a rendered picture, it must have a resolution. If reality is indeed rendered on demand, this hints at its digital nature. But our world seems smooth and continuous. Where is the evidence of its discreteness? Our intuition describes the world as analog, like a vinyl record with a continuous groove that can be divided infinitely. However, all of 20th century physics, starting with Max Planck, screams the opposite. In 1900, in an act of desperation, he proposed that energy is emitted not in a smooth flow, but in discrete packets, or quanta. The world turned out to be more like an MP3 file, a set of discrete samples. Physicists may have already found the minimum pixel of space itself. Its size is called the Planck length, and it is the most compelling evidence that we live in a world with a finite resolution. Any digital image, no matter how realistic it looks, breaks down into pixels when magnified. What if the very fabric of reality has the same fundamental resolution, a limit below which one cannot go? This minimum unit is 1.6 by 1035 meters. To measure anything smaller than this Planck length would require such colossal energy that it would collapse into a black hole, destroying the very object of measurement. This is not a technological barrier, but an absolute physical one. Space is not infinitely divisible. It has an indivisible quantum. This is exactly what we would expect from a simulated, computable reality, and it directly contradicts the idea of an analog universe. This is the pixel of our matrix. But space is only one coordinate. What about time? If space has a minimum pixel, could there also be a minimum frame, an indivisible quantum of time? Yes, it's called Planck time. This is the interval it takes for light to travel one Planck length. But this is not an isolated case. All of modern physics is built on the idea of discreteness. Energy is transferred in portions, or quanta. Light is composed of particles, photons. Smooth analog transitions do not exist at the most fundamental level. And this leads us to the answer, why is the universe discrete? Because any computational system is inherently discrete. It operates in finite steps, or processor ticks, not in an analog infinity. Reality doesn't change smoothly, it is redrawn at an incredibly high, but finite, speed. And this idea was born long before powerful computers existed. Who first dared to suggest that our entire reality is the result of a giant computer at work? In 1969, Konrad Zuse, creator of one of the first computers, proposed the hypothesis of a calculating space. Back then, it seemed like a brilliant but marginal fantasy. But today, theoretical physicist James Sylvester Gates, working on the equations of supersymmetry that describe electrons and quarks, discovered structures within them identical to error-correcting code. The very same code your browser uses to transmit data without errors. The search for the pixel of reality and the code of the universe is no longer philosophy, but the cutting edge of theoretical physics. Physicists weren't looking for code. They stumbled upon it within the mathematics that describes the world. This brings us to the most obvious question. If the world is digital, why don't we see its pixelation? If reality is made of pixels, why do we see the world as smooth and continuous, rather than grainy like an old photograph? The answer is simple. The Planck length is so small that to us, the world appears perfectly smooth, like a display with an incredibly high resolution. We cannot magnify reality enough to see the pixels themselves, but we can observe and describe the laws by which they interact. These laws, the physical constants and equations, are universal, unchanging, and most strikingly, described in a single language. That language is mathematics. Its unreasonable effectiveness is one of the strongest arguments that reality is not just described by mathematics, but is itself a mathematical structure. In other words, it is code. We don't see the pixels, but we see the code they are written in. This turns physics into cryptanalysis, an attempt to crack the source code of our universe. Why does mathematics, an abstract mind game born in the quiet of studies, so flawlessly describe everything from a falling apple to the structure of black holes? We see its simple manifestations everywhere. The number pi is hidden in the bends of rivers, and the Fibonacci sequence governs the growth of sunflower spirals. This creates the illusion that we are simply finding a convenient language to describe visible patterns. But everything changes when we delve deeper. In 1854, Bernhard Riemann developed his abstract geometry of curved spaces as a pure mathematical fantasy. Half a century later, Einstein discovered that this very tool, already prepared, perfectly described gravity. This doesn't feel like an invention. It feels like a discovery, as if archaeologists found not just ancient pottery shards, but an instruction manual for the universe. And this manual has preset factory settings. These settings, fundamental constants like the strength of gravity or the charge of an electron, are chosen with unimaginable precision. Change any of them by a tiny fraction of a percent, and the universe would become a sterile wasteland without stars, planets, or life. There are two explanations. First, there is an infinite number of universes with random laws, and we just happen to be lucky enough to be in one of the few viable ones. Second, these parameters were intentionally set by a creator. From a statistical standpoint, a single act of intelligent design seems no less probable than an infinite number of random worlds. The fine-tuning looks less like a cosmic lottery and more like a program's configuration file where it's written, gravity equals 9.8, life enabled. It's like finding a radio receiver perfectly tuned to the only station in the entire band. It's more logical to assume someone turned the dial than to think it randomly stopped in the right position. But could this code itself, the mathematics, contain proof that we are inside a closed system? In 1931, mathematician Kurt Gödel shattered a 2,000-year-old dream. His incompleteness theorems proved that in any sufficiently complex system, like arithmetic, there will always be true statements that cannot be proven using the rules of the system itself. This is frighteningly similar to the situation of a video game character who can never prove the existence of a world beyond the screen using only the physics of their game engine. Gödel's theorem is not just a mathematical curiosity. It may be a fundamental systemic limitation of our reality, a built-in rule that says you cannot fully understand the system while you are inside it. But these fundamental laws are unbreakable, unlike the user interface of our reality. If our world is a program, it must have errors, bugs, glitches. Can we notice them? The standard answer is that déjà vu, strange coincidences, and false memories are just glitches in our brain, an unreliable witness. But what if the error is collective? The Mandela effect is when thousands of independent people clearly remember events that never happened. This is too large scale to be a simple individual memory failure. What if it's a glitch not in our hardware, the brain, but in the software, reality? Perhaps these are artifacts left after the installation of another patch, traces of old files being overwritten. This transforms us from patients with poor memory into witnesses of a system error. Thousands of people remember a world that was slightly different. Is it mass delusion or a bug in the code of reality? Take the most famous example, the monocle on the Monopoly Man. Thousands of people remember it in minute detail, but it never existed. Psychology explains this as confabulation. The brain doesn't record memory but reconstructs it, and we collectively fill in a logical detail. The internet only amplifies this misconception. But what if the glitch isn't in our hardware, but in reality's software? What if it's a retroactive patch that changed a minor detail in the past? The strangest thing about the Mandela effect is not the error itself, but the crystal clarity of the false memory, as if people remember a previous version of the world. And this isn't the only glitch. There is another, much more personal one that the system generates directly in our consciousness. What is déjà vu? A fleeting but absolute feeling that you have already lived this exact moment. Neuroscience says it's just a lag in the brain, a desynchronization between hemispheres where a real event mistakenly hits the memory center a split second before it hits the center of awareness. But what if it's not the brain that's glitching, but the system? Then déjà vu is the moment the program mistakenly loads a cached file of a future event right before rendering it in real time. It's not a perceptual error, but a data leak. And if that's the case, the future has already been calculated. Your feeling that you know what someone is about to say isn't mysticism. It's you reading an already loaded, but not yet played, audio file from the simulation. Why do coincidences occur that seem too perfect to be random? You think of a person, and they call you instantly. The law of large numbers states that in a world with 8 billion people, an event with a 1 in a million chance happens 8,000 times a day. It's not a miracle, it's statistics. But there is another explanation, a lazy simulation. To save resources, the system doesn't create unique content for everyone, but reuses existing objects and scenarios. Meeting a doppelganger isn't mystical. It's the system using the same 3D model in different locations to save RAM. Seeing repeating numbers on a clock isn't a sign from the universe. It's an idle cycle of the system scheduler. All these glitches are just cracks in the wall. But beyond them lies the wall itself. If all these bugs are real, why can't we use them to hack the system? Because any complex program has foolproofing and self-correction mechanisms. These glitches are just an acceptable level of error, but we don't need to hack anything. The most important and unbreakable limitations of the simulation are in plain sight. We just call them by the wrong name, fundamental laws of physics. They are not properties of the universe. They are rules of the software code. The speed of light limit is not a cosmic barrier, but the maximum data processing speed of our universe's processor. In 3 minutes, you will learn why the most important law of physics is actually the main technical specification of our server. In an infinite universe, there is an unbreakable speed limit. Why? Einstein gave an elegant answer. The closer an object gets to the speed of light, the more its mass increases, requiring infinite energy to accelerate further. This is the law. But what if it's not a law of nature, but a limitation of the system? The speed of light is not a physical limit, but a computational one. It is the maximum speed at which our reality's processor can calculate changes and transmit information across the grid of space. All the strange effects, like time dilation, are not mystical, but are rendering artifacts that occur when the system operates at its performance limit. We don't live in a universe. We live on a server where the global ping is 299,792 kilometers per second. And this isn't the only technical specification in our world's documentation. Other laws of nature are also lines of code. Take the law of conservation of energy. It is neither created nor destroyed, only transformed from one form to another. Why? This sounds less like a property of nature and more like a basic rule for a stable program. The global variable total energy must remain constant to avoid errors and the crash of the entire simulation. This isn't a discovery, it's reading the technical documentation. The same logic applies to the law of conservation of momentum, or electric charge. These are system invariants that ensure the world's stability, and the discreteness of energy, its quantization, is a direct consequence of a digital system that cannot operate with infinitely small analog values. If the system has such strict rules, it must also have a creator. If we are in a simulation, who created it and why? The simplest answer comes from Bostrom's trilemma. We are most likely an ancestor simulation, created by our distant descendants to study history. This gives our existence a scientific purpose. But reality could be darker. Perhaps we are just data points in someone else's experiment to test the fine-tuning of the universe. Or even worse, characters in someone's hyper-complex video game. We may never know the truth. As characters inside a program, we don't have access to the source code. Any higher power, any god in this paradigm, is just a system administrator with access to the command line, able to change variables. This knowledge both devalues religions and explains their emergence. We started with the cold logic of a philosopher, delved into the ghostly world of quantum physics, searched for the pixels of reality, deciphered the language of the universe, noticed bugs in our experience, and ran into the iron walls of system limitations. Individually, each of these clues can be disputed, but their true power lies in their synergy. These are not 6 different stories, but 6 chapters of one. Bostrom's logic predicts what quantum physics finds. The processor's limitations are perfectly explained by the pixelated structure of space. The bugs are artifacts of a system written in mathematical code. When all the evidence points to one suspect, it ceases to be a coincidence. The puzzle is complete. Now the main question, if all this is true, how should we live our lives? It's time to choose your pill, the red one or the blue one. Let's assemble this machine. The 2 most solid pieces of physical evidence, the pixel of the universe, the Planck length, and its processor, the speed of light, are not 2 separate facts. They are 2 specifications of the same hardware. In any digital system, the screen resolution directly determines the maximum speed at which information on it can be updated. One is meaningless without the other. It's like talking about the speed of your perception without knowing the density of nerve endings in your fingertips. The denser the receptor pixels, the more data there is to process, which in turn sets the speed limit. Our hardware has clear, measurable, and interconnected technical specifications. This moves the hypothesis from philosophy into the realm of reverse engineering our universe. But any hardware must have software. And this software is written in the language of mathematics, with its main principle being brilliant optimization. The quantum observer effect ceases to be a paradox and becomes a classic programming technique, rendering on demand. The system doesn't waste computational power on what the player doesn't see. It simply keeps objects in a state of mathematical probability until a request is received from an observer. This works like our dreams. The brain doesn't create the entire dream world in detail. It generates only what your attention is focused on, while the rest exists as a vague potential. The software of our reality doesn't build the entire universe at once. It renders only the part we are interacting with. But who wrote this code, and why does it sometimes glitch? The answer lies at the very beginning of our investigation. The cold, abstract logic of Bostrom's trilemma predicts precisely this kind of world, one that seems real but contains minor artifacts and glitches that betray its artificial nature. Our personal experiences, like déjà vu and the Mandela effect, become empirical confirmation of this philosophical conclusion. Now, all 6 clues align into a single, consistent system. Bostrom's logic requires its existence. Physics describes how its hardware and software work. And our personal experience allows us to notice its bugs. What we have is not a set of coincidences, but a complete picture of the world. And it poses one final question to each of us. What do we do with this now? Ultimately, it doesn't matter much whether the world is real or simulated. What matters is how we live it. This knowledge can either break you or set you free. On one hand, you can feel like a prisoner. The realization that your suffering and achievements are just lines of code can lead to despair and apathy. This is the path of powerlessness. On the other hand, you can become a player. If this is a game, it has rules that can be studied and goals that can be achieved. This is the path of exploration and finding meaning within the system. After everything you've learned, which do you feel you are? Write just one word in the comments, player or prisoner. There is no right answer. There is only your choice. Let's see which one of us is more numerous. Perhaps the very purpose of this grand simulation was to see which choice we would make.